Hello, good morning. Please let me know if you can see the screen and hear me well.
Good morning. Yes, we can see the sky. Thank you.
Thank you. So, thank you guys. Today I'm going to be talking about the SD Core and the Aether projects, providing an overview of them. This is going to be an introduction. Most of here the slides are from previous presentations from the SD Core and the Aether teams. So thanks all of them for their contributions. First, I'm going to introduce the SD Core project. SD Core is an open source dual mode 4G and 5G mobile core. The goal of the project is to enable connectivity as a service. The architecture of the project, if you take a look, it provides two control plane, one option for 4G and another one for 5G, and the implementation of a dual core user plane function. It means that UPF function can be attached to a 4G or a 5G core control plane. The whole architecture of this components is proposed to be fully disaggregated. It means that the components both here in the control and the data plane can be composed of containerized components. It means the functions from the 4G and 5G core can be decoupled from each other. The project supports 4G and 5G standalone and non-standalone. It's important to mention that the application of the northbound of the SD Core project allows that the settings of the cores can be configured in runtime via extensible set of APIs. Think here, for example, network slices in the case of 5G. The goal of this project is that they can be consumed then because they're fully programmable in runtime. They can be disaggregated and put in a close to a cloud native architecture. They can be consumed as a cloud managed services. Think here that there are definitions of settings here, Helm charts, and let's say Kubernetes manifest that can deploy these components in Edge Cloud to be operationalized by a Kubernetes cluster. The point to take in here is that both projects, let's say sub-projects inside SD Core, the 4G and 5G, and so the UPF, they follow 3GPP standards. It means that each one of the functions, even inside of the 4G and 5G core components, provide interfaces that can make them be consumed separately as a part of, let's say, a multi-vendor kind of like mobile core deployment. So if you take a detailed overview of these projects, the SD Core on one side here, you see on the top, in red, you see the 5G core part of it. The 5G core part of the SD Core was provided by a free 5G core. This was like an initial code that was seeded to the project. And on the bottom side, you see the 4G core control plane. And this set of functions came from a previous project in ONF called OMAC. The 4G core, it is fully compatible with a release 13, and there are other functionalities from later releases that were implemented in the core control plane, as they were needed by the project itself, by the development of features, not only in SD Core but also in the Aether management platform that I'm going to be talking later. The same for the 5G. The 5G is compliant with release 15 of 3GPP, and there are other features, for instance, from release 16. You can check this in the release note of the project. that provide certain features that were customized by the developers. Again, both of these components, the 4G and the 5G control plane, they can be deployed as Kubernetes, let's say, manifest in a Kubernetes cluster using Helm charts that allow full configurability of the components. And the same for the UPF. I'm going to be talking later about this component in particular. UPF is particularly not part of SD Core project. It is part of SD Fabric project, but I'm going to give an overview of it as well. So to talk a little bit about the SD Core releases and a little bit of the details of what's happened is that since OMAC and this free 5GC were seeded into the SD Core, let's say, project as a whole, there were 2 releases since then, 1.0 and 1.1. SD Core 1.0 was released in the end of last year, 2021, and this is a release that this one and the 1.1 were validated on production sites. Those production sites were not only were part of the internal, let's say, ONF 4G deployments and that it had, and also from the Pronto project that ONF is developing or was developing with universities in the United States. There is a documentation site that was created and later in the release on 0.0 and updated in 1.1 that presents comprehensive details about the project. It means that it provides a way that how each one of these components can be configured, both the 4G and 5G control plane. It means the configurations of the Helm charts, their versions and their releases, and their specific configuration of their, let's say, settings or their values that can be highlighted to point, let's say, a good developer guide of different functionalities in each one of these cores. And that specifies as well each one of the features that each network function, let's say in the 5G, for instance, the AMF support when it's regarding the 3GPP compliance, and the release note details each one of these features. So it's important to say that in these SD Core releases, there are configuration APIs, as mentioned previously. These configuration APIs, I'll explain them later, but they allow the delivery of certain custom features in the 5G and 4G core that is regarding application filtering and multi-level QoS metering that were, for instance, used in the Aether management platform. And that was part of, for instance, for the 5G stable version that was available in the Aether network. And finally, one of the most important things of the SD Core project is that it lately provided a gNodeB simulator that is available for 5G testing. So if we take a look at a little bit about the deployment options of a 4G and the 5G control plane and the SD Core project as a whole, we can see that in the model of the Aether platform, the goal of the project is that both of these 4G and 5G cores can be deployed in a central cloud. Think here, for instance, as a hyperscaler cloud, a public cloud, and this cloud can be connected to multiple sites or edge clouds. Think here, for instance, multiple enterprises, where the data plane function of the 5G and or the 5G core can be instantiated. And the goal is that the same control plane that runs in a central cloud can be multiplexed to handle traffic management, let's say control management of UPFs in different edge clouds. So the important aspect is that this deployment option is available, but at the same time, it's possible to also deploy the 4G core and 5G core at the edge cloud together with the UPF components. So as a full, let's say, 5G or 4G standalone component or full function. So, and the point of these deployment options is that the UPFs in the edge sites, they can be multiplexed for different use cases. Think here, for instance, as network slicing 5G case. The architecture of these deployment options is only achieved because of this, let's say, CUPS architecture, control user plane separation, where the 5G and 5G core use the PFCP protocol, is a protocol specified by 3GPP that defines the connectivity between the UPF and the core control planes from the 4G at the same time as the 5G. So this one of the features that these deployment options allow is that the UPFs can be added in runtime towards the where the UPF itself can trigger the association with a particular core. So think here that, for instance, if there's a single core control plane and there's the need to scale the deployment of the data plane, multiple UPFs can be enabled in the data plane or in the environment, in the edge cloud here, for example, as the workload goes on, and that can be also configured in runtime. So the same goes for the let's say the stop or the removal of these UPF components. They can be added and removed in configured in runtime. So at the same time, you could have, for instance, multiple edge sites added to the same, let's say, central cloud, but you could have also these edge sites removed. And the SD core has the proper capabilities to handle this add and removal of UPFs. And it's important to notice that there are different, as mentioned, the UPF was part of SD Fabric project, is part of SD Fabric project, and that it has its own releases and its own features in it. And the goal of this communication between user and control plane is that it is made backward compatible. So it means that you can have UPFs from enabling 4G or 5G data plane connectivity in different versions and different releases, enabling different features for the control plane. Here is just a more detailed overview of the UPF. As mentioned, one control plane or 4G or 5G can be enabled to handle multiple user plane functions, depending on the application needs. I mean, here the application is of the core itself. And the UPF component, it can exist in the SD Fabric as let's say, two forms of instantiations. One is called BES UPF. This is based on the software switch, name it BES, where the UPF component is virtualized. It means that it can also run as a containerized component in a Kubernetes cluster. So this BES UPF, it can be deployed both in the public cloud or in the edge cloud, and it presents throughput of certain about 100 gigabits per second. The point of this UPF is that the latency, I mean, latency, as long as latency is not a concern, it means that this UPF could make the functionality available for this kind of bandwidth, deployed, for instance, or in the edge cloud or in the public cloud itself. On the other hand, the P4 UPF is a version of the UPF that was developed using the P4 programmable language. It means that it's enabled by a hardware switch that supports a P4 language, and this implementation actually conceives throughput in terabits per second, and it's much more, let's say, defined for performance applications. The point is that as multiple UPFs can coexist in not only in one edge site or in one deployment environment, as well as in different ones for the same core, the control plane selects the UPF on diverse set of criteria. This was defined by the 5G, where it allows the definition of UPFs based on the slice, for instance, slice ID and SSAI, for instance. But in the 4G control plane, it does not have this abstraction of slice. So the SD Corp development team created an abstraction that it is possible, for instance, to select UPFs based on their APN field. I think here's like a network definition field of the gNodeB and the core. And finally is that the UPF, as mentioned before, what allows this this architecture to be so much, let's say, programmable in runtime and let's say scalable, is that the UPF was defined to have a functionality of initiating the association from itself to the core, to the control plane. Here I'm just gonna provide you an overview of these two projects, the BES UPF and the P4 UPF. In an overview, what we have is that the P4 UPF on this the left side here, it's based on the let's say a P4 enable switch or programmable switch, hardware switch here in this case, where you have a P4 pipeline is written in the P4 language, specifically designed for the UPF functionalities. You have also that this P4 is enabled by a UP4 application that is running in the onos controller, that actually is the one that receives the information of the rules that need to be created by the PFCP agent that are programmed by the 5G or the 4G core. On the other hand, here we have the BES UPF. It's a containerized, let's say, packet processing and forwarding function that can be run in a Kubernetes cluster in the means of a virtualized network function. And the only requirement here for this is that the existence of this, let's say, network function is the communication with a PFCP agent. There are some specific functionalities, for instance, for each one of them, such as, for instance, the BES UPF. It can be deployed with different requirements from the hardware, such as it can be enabled by SR-IOV functionalities in the NICs, or it can be deployed, for instance, in a single interface using MAC VLANs. But these details are in the release notes in the SD Fabric documentation and SD Core as well. And there you have the deployment options and deployment documentations well written. I don't want to get into too much details here. So back to the SD Core project, the idea of this programmability of the SD Core is that the SD Core himself, as you can see here in the blue, let's say square, is that it is seen as a black box itself. That everything that's inside and all of these functionalities can be programmed by entry points. In this case, REST entry points, for instance, for the programmability of the network slice. And there's that, in that case, it provides a network slicing API programmable interface. And similarly, it provides a subscriber provisioning API. And what does that mean is that in runtime, it's possible to define the addition, the remove, and the modification of subscription elements. And for instance, let's say subscription users. Think, for instance, here a subscription, it means a UE, let's say a handset attached to the network, and that network and that UE has some information related to it. In this case, a specific subscriber ID, for instance, MIC is the acronym for that, and that can be programmed with the specific parameters to be allowed to be accepted into the core attachment procedures, for instance. The same goes for the network slice. There are specific APIs. They're well detailed, their models in the SD core documentation, but it allows that the network slice can be defined and then defines a pool, for instance, of UPFs that belong to a certain slice, and the set of subscribers that can be configured to have a certain association with a particular slice. And then finally, in a very important aspect of this is that the SD core project provides functionalities that allow the extraction of metrics from the functions themselves to a time series database such as Prometheus here. In a way that, for instance, it's possible to see the status of the connectivity of a particular UE in the AMF component of the 5G core. Talking just a little bit about the gNodeB simulator. The goal of this simulator is actually to trigger automation of tests. The goal here is that it can provide a control plane verification of messaging between the SD core components and the gNodeBs and the UEs that the simulator provides, and as well as data plane, very simplified data plane connectivity here in the UPF to the gNodeB and the UE instances. So in this case, the goal of this gNodeB is to, as mentioned, enable the automation, for instance, sanitary traffic tests. That means that it is going to trigger specific 3GPP procedures, such as a UE registration, the initiation of the UE PDU session, the registration, and specific trigger of traffic between the UPF and the gNodeB, to see the functionalities that are provided by the core are actually being implemented. There's in the development cycle of the gNodeB, the idea is that in the future that the goal is to specify that specific applications here in the UE can trigger traffic with another application servers in the other hand, on the other side of the UPF, for instance, let's say the internet. This is in development. There is a complete documentation about how to deploy the gNodeB simulator, how to trigger the tests, and how to check the automation of these tests as well. So in a way that a developer that is deploying SD core in its own notebook, for instance, its own environment, a Kubernetes cluster, let's say, can develop new features, prototype them fast, deploy them, and trigger their validation with a gNodeB simulator in a single environment. It's important to talk when talking about the project itself. It's important to talk about mostly specific about the quality assurance environment for testing of these functionalities. Besides of having the SD core project as other ONF projects have, there is a CI/CD pipeline where we have the checkings of, like, for instance, licensing and unit tests for each one of the functions of the projects, where this comes from a particular project HEPO before a merge and a review of the components and each one of the artifacts of these components. For instance, the Helm charts or the image repositories like the Docker images here. In the one of the cycles of the of the delivery, or let's say the delivery of the components in a, for instance, in a execution environment. The testing of the quality assurance is done using NG40. For instance, it was defined using that for triggering end-to-end, and also using the gNodeB simulator to trigger end-to-end test connectivities and a myriad of 3GPP compliant procedures to verify, for instance, the workload of the core. And that was specifically validated in for instance, in night tests running every day according to the new releases of each one of the functions of the project in the 4G and in the 4G and 5G control plane. So to give a overview of the project itself, then and is that the project itself came from Free 5G and OMAC. There was a lot of features that came added by the SD core development team, such as the configuration via these APIs for the subscriber and for the network slicing. One of the highlights is that in the SD core, for instance, release 1.0, this test and then the quality assurance provided that the 5,000 subscribers could connect attach with 10 calls per second stability in a single instance of a deployment. There were important fixes that came after especially the 5G core that came from the UPF connectivity. Think here, for instance, that in edge clouds connecting to central cloud or hyperscaler cloud, the UPF had some latency in the connectivity of the PFCP agent, and those were properly handled by the architecture for adding, removing, and modifying UPFs in a particular association with a core. There were cases where, since these components were designed to be in a cloud managed architecture, there were cases when the network functions were restarted and they triggered many errors in other functions themselves. So there were a lot of fixes in the projects to make this restarts of the network functions, each one of them. For instance, if the SMF is restarted, the AMF is restarted in 5G, it does not compromise the execution of the other functions. And the configuration APIs, they can trigger the configuration of these network functions as they are restarted. So there is a specific configuration function that maps the configuration for each one of the internal network functions of 5G and 4G. There were different integration tests and N1 interface. It means the connectivity between the core and the UE that were modified or enhanced to support, for instance, different UEs, different types of handsets, that in a way that we had some stability on that. And it's important to mention that, as initially mentioned, the SD core project was deployed in production in the Aether network. There were different edge networks with 4G and 5G. For instance, in the Pronto project, but also in 5G in the case of the SD run trial that was deployed in Deutsche Telekom with an actual 5G, let's say, or run compliant radio access network. All of the details of the architecture components, the manuals of installation, the details of the architecture, how they work, can be found in these resources here. And in the SD core dev channel in the ONF communities, like the SD core development team and others from related to it answer questions about the deployment, the verification, and the development of the SD core components. So feel free to reach out to this team here and ask questions about the resource in these components here. Now I'm gonna be talking about Aether and how Aether is related to SD Core and also the SD-RUN project. As mentioned, I'm not gonna go into details about the architecture and all of that, but just provide a high-level overview of the components and how they are associated with each other. So Aether is a platform that was designed to be an enterprise 5G and 4G edge cloud as a service platform. So it means that it was designed to provide the approach that you have different kind of like applications or use case in enterprise networks. One of them being the connectivity itself, for instance, for 5G small cells. And the goal is that Aether would provide the means to deploy and configure and manage edge sites as well as central clouds by a management platform in a way that the different projects that ONF has, for instance, SD-RUN, SD-Core, and SD-Fabric, can be operationalized by Aether. In this case, providing connectivity, but as well the means to consume the APIs of these projects and provide these APIs as a single entry point for edge applications as well as cloud, central cloud applications. So to provide examples here, think for instance that you have cameras or IoT device that are connected to a 5G network, let's say through ORAN compliant component, radio access network controlled by the SD-RUN project. In that case, the connectivity in the edge provided by the SD Core user plane. And important here is that the Aether platform allows, for instance, a breakout at the remote Aether edge sites, where you can have actually edge applications running and consuming traffic locally regarding, for instance, low latency requirements for this specific application. At the same time, this platform allows that similar applications or applications that do not require some restricted latency requirements to be ported to the cloud, from where the core and instances of the mobile, the 4G and 5G core control plane can be instantiated, and there you can have, like, for instance, heavy loaded applications running, such as heavy AI and machine learning applications. To put in context of the other projects, the overview is more similar to this. So you have the aspects of the applications, the connectivity being provided by the network itself, operationalized by, for instance, possibly by the SD-RUN project, where you have the control of the ORAN elements here in the edge of the network. And you have the edge network being operationalized by the SD-Fabric components for the data plane connectivity, and the SD Core as providing the means to connect these cells from 4G and 5G, and in the central cloud as well. And on top of that, there is a Aether ROC, what is called the component, means runtime and operation control. Is the actual a core part of the Aether platform that provides the means to consume and program the APIs of each one of these projects offer from the edge towards the central cloud. And the important aspect here to highlight is that these edge sites can coexist, as mentioned in the SD Core presentation, with multiple edge sites can coexist with a unique central cloud as a deployment option. And here's a more detailed overview of this, let's say, design API and design architecture of the Aether management platform, where you have different applications running on the enterprise edge, for instance, on premises, And when you have the deployment of all of these components that are deployed over a Kubernetes-based cloud, in his case, for instance, SD-Run and SD-Fabric and the SD-Core data plane. And these components allow connectivity and other functionalities, such as the in-band network telemetry provided by the SD-Fabric project, to be exporting metrics and have these metrics consolidated in a single point of entry in the cloud, in a hyperscaler cloud, from where the runtime and operation control can see those metrics not only from SD-Fabric but just also from SD-Core and SD-Run, and have the control over them. Sorry, just a second. I'm gonna get the charger off my computer. Got it. So thanks. Sorry for that. So back to the presentation. The idea of the ROC here is that it can present as a single operator portal or even enterprise portal in a way that all these APIs from each one of these different projects here can be exported and controlled by it. And even better, this ROC also can offer a consolidated set of APIs for applications running both in the on-premises edge or in the hyperscaler cloud. And I'm going to give you an example of one application that was developed in this case. Here is just example of the deployment option for Aether. In that case, it's just detailing that a central cloud, for instance, running this Aether management platform with a ROC component, can let's say manage and operationalize different edge clouds, or in this case, for instance, different enterprise edge sites, running their own versions or own release of SD-Run, SD-Fabric, and SD-Core components, and providing, for instance, connectivity of different network slices from the edge to the cloud. And the important aspect here is that each one of these slices could be multiplexed by different UPF functions running in the edge, as well as directly connected to different applications running in the edge and also in the central cloud. So how does that happen, and what are the intersections actually of that? This is just a building block, kind of like a diagram that details a little bit about that. We have on top of the components, we have let's say that are provided by Aether itself is this hybrid cloud management and operationalization tools for the deployment of these components in the edge cloud provided infrastructure or in a hyperscaler infrastructure. So if we go to the technical level, it means a set of a CI/CD pipeline for triggering configurations of the infrastructure here in the hyperscaler cloud or in the edge cloud. Think here, for instance, a set of automated scripts for triggering Terraform and Ansible configurations of the infrastructure. And when that infrastructure is deployed and the Kubernetes cluster is operationalized, the components themselves can be deployed, and the Helm charts of them are specifically configured, can be specifically configured for each one of these environments. So think here, for instance, that you could have a specific version of SD-Fabric or the UPF, P4 UPF running in particular edge cloud, that is connected to a 4G or a 5G SD-Core component running in the edge or in the cloud, and a specific version of the SD-Run as well component, controlling O-RAN small cells in the case of enterprise networks. And both of them or all of them controlled by runtimes and operation control component. So how does that happen actually in the aspect of the ROC? The ROC is a component that provides this access of portals for the operator and the enterprise. There's a interface for that. There's a REST that it provides the access of this REST interface. And there's a particular definition of the models here that are supported by this REST interface. And these models actually conceive what is defined in the Aether config. Or this is just another reference to onos-config component. And the goal here is that the ROC can program multiple adapters, and these adapters, each one of them, they reference different models here in the Aether config. And these models enable that each one of the adapter translates the configuration that is triggered by the Aether config in each one of the particular services. Think here that a service in this architecture would be the SD core components, the SD fabric, or the SD run. So it allows the end-to-end, let's say, programmability of the components of the Aether architecture. These components as well allow the triggering of metrics and events to a repository. In this case, the architecture was using a Prometheus database, where there were analytics engine to analyze the logs and the information about that and export to Grafana that could Grafana dashboard that could be seen in the portals. The same case here, the models could be used to trigger as well workflow engines that a workflow engine that would trigger the let's say specific lifecycle management of the components in the architecture in the cloud, let's say, managed architecture. For instance, think here as the scaling of a component that was triggered in the configuration here from the northbound would trigger the workflow to scale the deployment of SD core control plane in a different cloud. And this is only enabled because of the onos-config architecture. And here is onos-config is a very important and core component here, very well designed, because it can it's based on gNMI, and the model plugins are based on Yang, and they using this onos operator abstractions, they can be loaded in runtime in a Kubernetes cluster. And the onos-config basically does is consumes the user definition of the models that are defined and programmed in the northbound to different or multiple targets using gNMI. And that allows that, for instance, you can have different adapters from different let's say domains here, run, a core, and fabric, using different model plugins to be configured by a single point of entry here in the northbound. To talk just a little bit about Aether deployments and examples of the applications that were deployed. Here, there is the architecture of one of the deployments, a high-level architecture that was, for instance, this is just an example of one architecture, of deployment architecture that was used in the Pronto project, and also presented in one of the demos that ONF had in the past with Aether. I'm just going to go through a high-level overview. This application was actually a 4G camera that was connected to the edge, and this 4G camera was connected through a 4G small cell, and that camera was going. The traffic of that camera was going through the edge side, and in the edge side there was an edge application responsible for detecting faces in the video input from the camera. And what happened is that the behavior of this edge application was defined based on the input from the camera, in a way that the edge application had access to the API of ROC. And what it did is that it could consume the programmability of the core metrics and also core functionalities to change the behavior of the network according to the camera. So the example was when there was no person detected in the camera by the edge application, the resolution of the traffic that was required by the camera was low. In that case, the edge application required in the network slice programmed by ROC for that camera to have no strict bit rate requirements. When the edge camera detected a person in the camera, that triggered that the edge application increased the resolution requirements for that camera to detect with a better, let's say, granularity the specifics of the person in that camera. And in that way, it triggered in the ROC the configuration of the better requirements for the network slice that was allocated for that camera, in which way that it improved the resolution of the traffic. And that was demonstrated as a person appeared and leave it let's say the scenario of the camera. Another one is like mentioned yesterday about the SD-Run, trial, outdoor trial that was hosted in Berlin in Deutsche Telekom. It was a setup of different partners to deploy, and that was centered mostly on the SD-Run project to enable the programmability of the run components. But what is important to mention is that all of the other components were part of the Aether management platform, and the operationalization of the setup, the edge cloud, the central cloud was done by Aether. In this case, that the person's operationalization of the edge cloud, the infrastructure, the installation of the components, the deployment, the check of each one of these components, the verification of their execution was done by Aether. And that was only possible because Aether, all of the sites that were deployed using Aether, they have a very well-defined CI/CD pipeline with the test automation infrastructure requirements defined here. One article that describes that really well, and the other one is about the automated CI/CD systems for Aether. Really well described in this other article here. And what happens actually is that Aether has a very well-defined CI/CD pipeline for quality assurance. Here, think about that there's a specific environment with Kubernetes cluster, with Aether deployments, SD core, SD fabric, and SD running integration tests that we're consuming the artifacts from each one of these projects. And once this quality assurance tests were passed, the deployment of the components took place in a staging environment where we had the definition of a soak test. And after those tests are like also passed, the check of these tests were passed, the components were ready to be released in production edge sites, such as the SD-Run trial in Berlin, for instance. Here's just an example of the CD system of Aether, where it had the different app configs defined in a GitOps manner from let's say GitHub repositories, and also the pod configs. That means the infrastructure configuration. Pod here it means a particular Kubernetes cluster in the edge or in the cloud, in the central cloud, and how the CD system was consuming the Helm repositories and the image repositories that were triggering the execution of Terraform and Ansible scripts to deploy the infrastructure. Here, the virtual machines, the routers, the VPNs, the Kubernetes cluster on top of them, and also the fleet controller that is this Kubernetes management, kind of like management platform for Kubernetes clusters that was deploying the fleet agent and deploying applications on top of it. And this is fully automated, this CI/CD pipeline. Finally, I'd just like to talk quickly about Aether-in-a-Box. I talked about Aether and all of that, but the way that the developers use Aether is that Aether-in-a-Box is a set of scripts that allow the definition of a cluster in a single machine, where the components from Aether can be deployed. And these components would be the SD core, for instance, and ROC, and all the other functionalities that can be consumed by ROC, such as Prometheus, let's say Prometheus database and Grafana dashboards. So Aether-in-a-Box is a way to define easy to develop and test environment and validate the installation of these components in a single machine. So a person can install this in their own laptop. And Aether-in-a-Box was also used to validate connectivity and basic tests in lab for proof of concept deployments with a 4G network, in this case with an actual gNodeB device and in a real UE handset. So both of these are well documented in the Aether docs and can be accessed, and all the instructions there for deploying Aether-in-a-Box in laboratories and for research purpose can be consumed there. This is all I had to talk today. My goal was not to get into details of the architecture components or the components themselves, but just to provide an overview. There's a lot of material to be explained for each one of these projects. And that is well detailed in the Aether and the SD core docs, and as well as in the case of UPF, the SD fabric docs. So feel free to reach out to the community in these Slack channels that were pointed in the presentation, and we're happy to answer the questions. So thank you.
Okay, so are there any questions inside?
Hi, Rafael. Thanks a lot for this very informative presentation. Can you give us some more information about the way forward? So what is next in your agenda with respect to Aether?
Okay, good point. So some information even before that is that maybe you guys are aware or not, but the whole ONF engineering team that was behind all of these projects, the engineering team was acquired by Intel.
And this is the reason of my question.
Yes. So I cannot disclose what is actually going to happen in these platforms or the development of them, but for instance, in the SD-Run and SD-Core, they're still part of the team and engineering efforts to make contributions in those projects. In the Aether management platform, that is going to still be decided.
Okay. I understand that you cannot say much about this, but that's really important for us because,
yes,
as you might know, Slices is really targeting open source solutions that are sustainable for us.
But the important point is that the source code is there, and it's fully open source, and the community is there to answer the questions as well.
Okay. Thanks again for your very informative presentation.
Thank you.
Thanks, Rafael, for the presentation. I have a small question regarding, because you mentioned that SD core is one part of Aether, right? And in the SD core, we have 3 5GC. So the question is this possible is this feasible to integrate OAI core with SD core and Aether from both technical and political point of view? Thank you.
From the political point of view, I don't see any issues. The projects are licensed in Apache 2 from what I remember. so the licensing wouldn't be an issue. The integration of the SD core is like actually 3.5G core code was seeded, but now each one of the repositories of the network functions are part of SD core, and so it contains its own repositories for those functions. And it's not that you need to deploy SD core with Aether. SD core can be deployed in a standalone manner. You can get the Helm charts, for instance, instantiate a Kubernetes cluster and deploy only SD core there, only the 4G core or only the 5G core. What the deployment that Aether allows is that these interfaces and this model that was defined by Aether, and I didn't talk much about that, is that in the SD core project was developed a SD core adapter. And this SD core adapter is what allows the translation from the ROC, from this component called ROC and this Aether config models, through the configurations of the SD core and the 5G and 4G, for instance, for programmability of network slices and subscribers. So if the integration is needed, I see two ways in the technical side to enable the programmability of this SD core adapter in OAI, for instance, using the REST APIs, or develop another API, another adapter that would be OAI adapter, for instance, that could define its own models to be consumed and programmed by the ROC. Is that clear? Did I answer your question?
Yeah. Thank you very much for the answer. And then in this case, we will reach out to you later to see how we can do that. Okay.
Yes, if I don't have the answer, I know someone who does. So yeah, please reach out, no problem.
Any other questions in the room, online? Okay, so no more questions. Thank you, Rafael, for your presentation.
Thank you again for inviting and the opportunity to talk here. And my apologies to not be there in person. Thank you, guys.
Thank you.